Hello everyone, welcome to this tutorial on fine-tuning BERT on the Amazon dataset to create a classifier. So I was having some technical difficulties recording a full-length video, so I'm just going to go through the code base here, which is not very complicated as opposed to that LSTM classifier. So of course, I started with downloading the dataset for the Amazon reviews dataset. So I have these two files, and I start by reading those text files, getting those lines, and constructing this dataset. Now we want to shuffle this as well, and this is how we shuffle, and then we obtain the shuffle lines and labels here. So some things that might not be familiar to everyone are maybe this unzipping operation and the zipping operation. So since we want to not lose the correspondence between the lines and labels, we want to first get them together. So what zip will do here is uh, it will wrap the first element of lines with the first element of labels, the second element of lines with second element of labels, and so on. So this way, when you apply a shuffling operation on the entire map set, the mapping, like the input to output mapping, is not lost. Now that we have shuffled the data set, we also need to unzip it. So this is how you unzip it. You just add a star in front of the mapped object, zip map object. And once we have the data set, we will create a training, validation, and a test part. And if you remember from the LSTM classifier tutorial, we wrapped our dataset around PyTorch dataset class. In this one, we will be using a different library. So we will be using datasets and transformers from Huggingface. So you can install them like this, and this part is nothing new. I'm just applying the same logic as last time. So we have the train, validation, and test parts. Then we wrap each of them around this dataset object, and then we wrap these three objects inside this dataset dict. So this thing is literally a dictionary of dataset objects. So that's why it's called a dataset dict. Hope that makes sense. So now that we have the raw dataset, we actually have the tokenizer. So this is how we can load the tokenizer. We import the auto tokenizer class, and we pass the name of the BERT transformer model that we want to use. And once we load the tokenizer, we can. So since we have wrapped this dataset around the dataset dict class, we can use this map operation. So what this mapping operation will do is it will apply this preprocess function to every example in the dataset, and it will give us an encoded version of the dataset. So let's see what this encoded version of the dataset looks like. So if we look at an example, so in addition to the raw text and label, we also now have the token IDs and the attention masks and token type IDs. So now that we have the tokens as well, we can move on to directly loading our model and training it. So loading is quite easy. So you just import the auto model for sequence classification module, and then you pass in the name of the model you want to train, and then you pass in the training arguments. So I can show you probably what these guys look like. Okay, let's just open BERT. So if you go to I should probably add a comment here. So if you go here, but actually not here. Yeah. If you visit this link, then you'll basically see all the different parameters that you can specify to the training arguments function. I can also show them to you here. So as you can see, it has like a zillion parameters you can pass. So I would recommend going through them at least once. I mean, I don't really know all of them myself, but some of them are useful, some of them are not. So I will be using only the ones that are specifically useful for this case. So first is the output directory. Where does it save all the models? Next is how often do we evaluate it? Every epoch, every iteration, or what? And then how often do we save the model? The learning rate, the regularization, lambda, and then this is warm-up ratio. So if you don't know what warm-up ratio is it's basically instead of starting with this learning rate right from the beginning, the model uses the first 10% of the training data set. So it starts from a smaller value, and then by the time it finishes reading the first 10% of the training data set, the learning rate would have been increased to 1e minus 5. So instead of starting from 1e minus 5 from the beginning, there's a gradual increase from a smaller value to a higher value. And this has shown to improve the stability of these models training, and it also leads to better performance. Now, the number of epochs we want to train this model for, and we also have this flag. So let's say we are training this model for 5 epochs, but the best model happened to be the one from epoch 3. So how do we ensure that by the end of this training, we have the weights for that model and not the epoch 5 one, which happened to be worse than epoch 3 one. So this flag allows us to load that best model. And how do we decide that something is best? We specify a metric. So in this case, we specify accuracy as the metric. And we'll also see how to compute this accuracy. We'll implement our own method. So now that we have the training arguments, including the learning rates, the weight decay, the batch size, the number of training epochs, we can proceed to writing the trainer. Now, one thing you might have noticed here is that we haven't specified the optimizer, and that's because there's a lot of black magic going on under the hood when you in this trainer. So this trainer is literally a beast that implements a bunch of different things. And if you really want to understand how transformers are fine-tuned, you should at least go through this function, this class once, and you'll get a good idea of how things are done in a well-developed project. And I can also paste a link for that here. Okay. Copy. Oops. Now there aren't many arguments to specify for trainer. So we start with the model. We call it backbone here, and then we specify the training arguments. Then we specify the training part, the validation part, we pass in the tokenizer, and then we pass something called the compute metrics. So this is where so whenever we enter the validation loop, this is the function that trainer will use under the hood. So this function is going to receive a prediction. And then first of all, we fetch the labels, the ground truth labels. Then we fetch the predictions from them. So red.predictions will give us the logits, and then doing an argmax over it is going to give us the actual prediction values. And once we have these two guys, we can use our old friends here to compute the precision, recall, F-score, and accuracies of the model. And we return a dictionary of these metrics. So what we specified here should be consistent with the keys in this dictionary. So for example, if you want to use F1 to decide which one is the best, which model is the best, we go with F1 here. Now, or let's say we call this thing as ACC, then we need to change it here as well. So the keys should be consistent. That's the main thing that we need to keep in mind. And let's try to train this thing. So once we have everything ready, um, we can train the model, and hopefully this works. Okay, so the training has started. One thing you might have noticed is this thing. Why did I need to add this guy? We needed to do this because by default, Huggingface trains on all the GPUs and it tries to use data parallel under the hood. So if you don't know what data parallel is, then what it basically does is it creates copies of the model, it creates copies of the data sets, and it distributes it across the different GPUs. So even though there's something called parallel, there's no true parallelism, and in fact that will take us a longer time to train our models. So that's why it's important to just pass it one to train it, run it on just one of the GPUs and not multiple. And yeah, so as you can see, like right off the bat, it has really good validation performance. And let me actually try to, or we can see. Yeah, so as you can see, like right off the bat, it has good validation performance, and it's going to save all the checkpoints here in this checkpoints folder. And yeah, now all that's left is to wait. So now we have finished the training process, and now we see at the end, we get a really good performance of about 80%. And the best model happened to be the one in the middle. Okay, so this is actually the model at the end of the third epoch, I think. Yeah, this is the end of the third epoch. So as you can see, so when we ran this trainer.evaluate, to run this model is in inference mode on the test set. It used this model, so the validation performance there was about 78, but the test performance was 80, so that looks all good. You can probably train this model for even longer times, like 10 epochs, let's say, but yeah, you can play with all the different knobs here. And if you want to use a smaller model, let's say, if let's say BERT doesn't fit here, you can go with distal BERT, or if you want to go larger, you can go with BERT large or things like that. So this code is all pushed and it's available on the PyTorch tutorials website. And the link is this. We'll find the code here. And yeah, that's it for this tutorial. I hope this helped. And good luck with all your tasks later on. Thank you for listening.